Alright, hello everyone, May the 6th. Alright, let's do this. What do we have today? Find the longest valid obstacle course at each position. You want to build some obstacle course. You're given a zero-indexed integer array, obstacles of length n, where obstacles I describes the height of the ith obstacle. For every index I between 0 and -1, find the length of the longest obstacle course in obstacles such that, For every index, find the length of the longest obstacle course such that you choose any number of obstacles between 0 and I. You must include the ith obstacle. You choose any number of obstacles between 0 and I. You must include the ith obstacle in the course. You must put the chosen obstacles in the same order as they appear. Every obstacle except the first. Every obstacle except for is taller than or the same height as the obstacle immediately before it. Return an array answer of length n, where answer I is the length of the longest obstacle course for index I as described above. Okay, so 1, 2, 3, 2. The longest valid obstacle for the first one is 1. For the second one is 1, 2. For the third one, 1, 2, 3. For the fourth one, so I want from 0 to I, where I must include 2, and you must put the chosen obstacles in the same order, and every obstacle except for the first one is taller than, so none of them should be taller than 2 for the last one. So it's going to be 1, 2, and 2. So the length is 3. Okay. So the second one is we have a 2, 2, 1, right? So if it's 2, that's just going to be 2. If it's this, so the last one is 2. So I need everything. It's like monotonic increasing, but not larger than this. So it has to be 2. The last one is 1. You have nothing. So it has to just be 1 by itself. So it's going to be 1, 2, 1, right? All right, third example, 3, 1, 5, 6, 4, 2. So 3 is 3 by itself. 1, because everything is bigger, so it's 1 by itself. 5, so I need to know 5 is actually going to be 2, right? 3 and 3, 5. 6 is going to be 3, 5, 6. 4, it's going to be 3 and 4. And 2 is going to be 2. So the answer shall be 1, 1, 2, 3, 2, 1. 1, 1, 2, 3. Oh, or 1. My bad. 2, 2. 1, 1, 2, 3, 2, 2. Did you find something? Yeah, I think I did find something. Let's see. So basically, I want to know for each one, what is the size of the monotonic increasing that's ending in this. If I know that, if I have something larger than that, then it's just plus 1, right? Yeah, just plus 1. If I have this, which is this one, this is smaller, so I need to find the largest one previously, right? That's smaller than this. So I need to find 3. So it'll be 3 is going to be 1. So 3 plus 1, so that's why this one is 2. Right? And then this, I need to find 1. So 1 is 1, so that one is 2. So on the other hand, what we're trying to say is, okay, let's do this again. 3, 1, 5, 6, 4, 2. I know 3 is definitely going to be 1. 1 if it's a decreasing, right? A decreasing, but I need to know something is larger than, well, I mean, can I put something like, let's say, sorted in the front? That would be hard. that you like need to keep something sorted. I can do sorted list, but that's like cheating. So let's try not to do that. So 1, I mean, if you do monotonic increasing, right? You can try monotonic increasing. So we will have 3 as first, and then 1. Monotonic increasing is everything you can try to pop, right? If I want to do monotonic increasing, oh, in this case it could be 3, 5, 1. Could be 3, 5, 6, or 1, 5, 6. Look, it has 2. Oh, you have 2 options. So basically, for 5, I can take 1, or I can take 3. Interesting. If we go monotonic increasing, so every time it's small, I'll pop everything. Right? So this is the smallest. So we know in the front we have something that could be bigger. What do you think? If we do it this way, I say I pop 3, now it's 1, and now we can do 5, and then we can do 6, and when I do 4, right? When I do 4, I'll be popping this, so it'll be 1, 4. But you cannot guarantee 1, 4. And we have 2, you can pop 4, now become 1, 2. But you cannot guarantee, right? Because I can think of a scheme where maybe I say 2, 3, 1, 5, right? If you do monotonic increase, you go 2, 3, and 1 comes in, you pop all these, and then 5, you'll say 5 will become 2, but 5 should be 3, right? So this method, how do I know I shall choose 5? That's a good question. And maybe we shall keep track. Because if I know, like 2 is 1, 3 is 2, 1 is 1, and then 5, right? I just need to know the largest one before. Is going to be 2, so 5 should be 3. The largest one that's smaller than me, right? The largest one that's smaller than me. Then how do I know which one is the largest one that's smaller than me? Among all the values that are smaller than me, which one has the largest? That is the question, right? I want to know among all the values that's smaller than me. If I know that, then it's become a very it's a very simple problem then. Smaller than me. If I if I have something larger, can we think about this way? If I have something larger, right? If I have something large in front of me, and I have something small behind me, right? If the large has some value, has a length x, then a small will never reach this value, will never be larger than this value, right? It's either the same as x, or it's even smaller, because we have like other larger ones, so it'll be smaller than this. Which means if I can, because I'm thinking maybe we can do a priority queue. Then we hit the largest value. But what if a smaller value comes in? Well, a smaller value comes in, yeah, that's not gonna fly. Unless you have a sorted list, so you can binary search it. But we don't have a sorted list. Good question. I'm stuck. What data structure should I use for this one? Maybe I shouldn't think this way because you're stuck, right? Maybe you shouldn't think about it this way. Maybe there are other ways to think. What other ways? What other ways? I mean, even if you use sorted list, it's not going to work because you need to find the largest value, right? You need to find the largest value that's smaller. Largest. So among all the values smaller than me, what is the largest? That's the question, right? What is the largest among everybody that's smaller than me? So we have a condition. They have to be smaller than me, and we want to know the largest value. If I know that, then we can say the largest value is smaller than that. It's going to be this. Now, how does that help, right? How does that help? Well, it helps if a new value comes in, right? If a new value comes in, if I know all the values before, yeah, that if you go one by one, it's O(n) squared. O(n) squared is trivial, but it's not the right way. Yep, no idea. All right, let's see. Binary search. Binary search. Binary index tree. BIT? BIT. Hold on. Let's read. So what is the problem? The problem is given an array, okay, and values at some positions. Now we given a new position. We want to find out the max value in all the positions smaller than the given index, right? What is BIT? BIT is, if I use a max value of BIT, right? If a query is from the start to this, give me the maximum value in here, right? And then, holy crap, this is BIT. BIT, yeah, the BIT dot update is your position and your value, right? Then what is update is, if we use a maximum, right, is from, we get a value of this, and then we say value, yeah, this is from start, right? We can say when we do BIT update, we can say, and then we do bit.query, because bit.query position is the max from 0 to position. That's bit.query. Isn't that exactly what you want? That's exactly what you want. It's bit.query. So we just need binary index tree. Let's give this a shot. Actually, I useful BIT. I forgot. Okay, BIT. I mean, this is BIT is for some, but we can definitely change it. Let me read this again. So BIT, n is the size of the range. Yeah, we need a range. But in this case, the range is just going to be the array length, right? Update value at the position by adding delta. All the other ranges that contains position, which means, yes, but in my case, it's gonna be update a new value, right? We update a new value, and when I update, I say, because the position keep going on, in as one base, this index is one larger. So yeah, it doesn't matter. So we do this, and then say this shall equal the maximum of original and the new one. And a query, some value in 0 to this. So if I stick to BIT, I think this one can be solved. BIT. Can you code it? Oh my god. It has a magic portion to it. And I is this portion. Do I know what it means? Maybe, maybe not. All right, let's try bit. N, right? Say self.bit equals 0 times n plus 1. I think that's the version I settled for. And def update self dot position, and we can say value, right? And it's a maximum bit. So if I remember right, we can do I equals position plus 1, and then we say should be while I smaller len self.bit. We say self.bit equals maximum self.bit and value. That's where we update this value. And I plus equal to, this is the magic, I and minus I. I have no idea. I forgot what this one. I mean, I know it's counting binary wise, but I'm not very sure. But that's the update. And update query, right? Query is just when a query to position, the maximum to this position. I equals position plus 1 while I larger equal to 0, we say, and probably have a result maximum. Everybody is larger than 0, so I can do 0. I say res equals maximum res and self.bit I. Right, so self.bit I, and I minus equal to I and this. So this is jumping back. All right, let's see if this is correct. I position plus 1. I smaller than that. Self.this. Doesn't matter max or not. I 0 plus equal to the max. I think that's correct. Right, return res. So that is my max. So when we do this, we need a max bit equal to bit line obstacles. Okay. Then we say for I ooh, that is not right. We want a value. It's not the length, it's the value. Because when I find 6, I want to know the bit from 1 to 6, 1 to 5. Right? I want a 1 to 5. So that is not right. This shall be I think maximum minus minimum. Right? I said this, the length is including min max is the total range. The total range. So it's to be the max of obstacles minus min of obstacles. I'll plus 1, just stay on the safe side. Okay, I'll plus 1 to include everybody. And then we can say for I, the position doesn't matter. I don't think the position matters. Because at each one, I just want to know a total smaller than me. What is the maximum? And in fact, if I have nothing, I think this shall be 1. This shall be 1. Right? Oh wait, hold on. Is it 1 or 0? So from this we can say from 1 to 2, right? From smaller to this. Oh, hold on. I think there's one more trick we need. This is the range, right? And eventually, when you do bit, you probably have to add. Hold on. Min O, max O. Let's get these out first. We might need them. Min or max. Thanks. Max minus min, right? That's the total range. And we say it's 1 based, right? So we start from 1 to the current range. Okay. So when I given a value, I need to minus the minimum. And then that will be the position. I will return, and that will be +1. So I think we shall start with 0. Right? And then for every 1 for obstacle, right, for in obstacles. So we want to find the currently what's the max value from the smallest to my current value, right? So we can say pre-max is gonna be max bit dot query your current obstacle minus minimum obstacle. All right, that's your position. This is your position. All right, this is your position. And once we're done, we can say, we can actually have a result is then this, right? And we can say max bit dot update. Then at your position, the value can be this +1. It's always going to be +1. Whatever the max, the previous, it can add yourself to it. So it will be +1. And once we do, res.append pre-max +1. All right, we just do this, and once we're done, we'll return res. Let's shake it out, see if this one works. I hope it does. I certainly hope so. And I like to throw in this, the ones I thought, 2, 3, 1, 5. Okay. That will be 1, 2, 1, 3. Obstacles. Longest obstacles. Maybe this is a something is not right. Something is not right. Hold on. What did I do wrong? While I. There we go. There we go. I have confidence that this one will be right. So this problem can be converted into this. Given a list and sum and values at some positions. Now, given a new position, what is the max value among all the positions that are smaller than the new position? Find that max value and the new position's value is that max value +1. It is designed for great solving using bit binary index tree. This is definitely an opportunity for us to revisit binary index tree. So I think I'll actually do it afterwards. But let's make sure this one is actually correct. And for that, I think might as well just throw some values in it. And check. See if it's correct. Yep, that is the result. I hope that is the result. That is the result. But Lord, it took so long, which means there are better solutions. That's good. That's good. At least we know BIT does work to solve this. But heck, it's slow. Because the value can be huge. I think that's why. Look at this. The value can be huge. 10 to the 7th. So this is 10 to the 7th. The time that's taken to create this array is humongous. It's humongous. Well, the performance is quite bad. Because the creation of BIT is the size of BIT, right? The size of BIT is corresponds to the difference between the max and the min of obstacles, which can be as large as 10 to the 7th. Yeah, that definitely slows things down. The mere creation of the bit array can be very slow. Thus, there must be a smarter idea, smarter solution. But BIT definitely works, right? All right, let's check the solution. Greedy and binary search. That's the one. Greedy and binary search. Do they have another one? Open login. Yeah, binary search, no, DP, that definitely. I guess it's not that hard, right? Based on how people versus. 1, 2, 2. Greedy. Find the longest non-decreasing subsequence. Do you know how to do this? Longest increase subsequence? I think I forgot. Wait, what's this? I must solve it before. Yeah. Dude, I forgot. I forgot the longest increasing subsequence. Man, this should be in the nightmare. I've solved it how many times? 1, 2, 3, 4 times. Dude, 4 times. You still don't remember. Lord. Yeah, I'm not able to solve this. 3 times before, but I wasn't able to solve it this time. Yeah, that is the longest increasing subsequence smaller or equal to a certain value. We must use binary search. Oh, binary search of a prefix monotonic array. Of course, we must use binary search. Yes, we want to sort it. I want to sort it so I know where to find. Yet we do not have a sorted array hand, nor is it possible for us to sort any array along the way. Exactly, that's the problem. We cannot sort the array along the way. Therefore, we don't know what is ahead of us. As we build a sorted array, an important observation is that if we want the sorted array to be as small as possible, such that it's more likely that we can append more values, to make that, we want it to be as small as possible. The value to be as small as possible. To make that happen, each time a new value is smaller than some value in the array that it can replace without changing the structure. Oh, we shall do it. For instance, given array 2, 3, 5, 7, and that is the current longest increasing subsequence. If we encounter 1, we can replace 2 with 1. Does this change the fact that the length of is 4? No, it does not. But what it does is that it lowers the barrier to create longer ALIs in the future. Let's say we have values happening after 1. By replacing 2 with 1, we open the door to accepting 2, 3, 4, 5, and thus creating an even longer ALIs. This won't happen if we do not do the swap. Okay, so I have an auxiliary, and every time I binary search the auxiliary and I do a replacement, right? This is where I find it, and if it's the same, I continue. If the current one is the largest, I append to it. Otherwise, I swap it. So that's the greedy part, right? That's the greedy part. So we're building it. As we read through, I want my longest array. Oh, so it's exactly the same as this problem. Is instead of returning this, we're returning every single step. Well, I honestly think this is more important than understanding BIT. I mean, in BIT, you can just say, you know what, I'm not 100% sure how that works, but I know that I can use BIT to solve this problem, right? But you do have this complexity. Time complexity is suffering because the size can be huge. But this is the one, right? This is the one. You're building the longest increasing subsequence, right? You're building it. And as you're building it, what you're trying to do is to make it as small as possible in every juncture, right? As small as possible. That you can imagine at this point, if we go back to some of the example, right? Let's go back to this example. So what we say is we have 3. Yeah, let's do this. Let's come back here. So let's go back to this example. Right, let me go to a new one. 3, 1, 5, 6, 4, and 2. So the auxiliary array, we have 3 to start with. Now we have 1, right? We want the longest increasing subset to be as small as possible, so we have more chance of appending new. So I say, no, I don't do this. Now it becomes 1. So for 1, the value is 1, right? For 5, I have to add 5 because I cannot swap. For 6, I cannot swap, right? Now for 4, I can swap because I can search this, and I know the current position for 4 is going to be this, right? And it's smaller, so I will swap it to 4, right? Therefore, for 4, so this is 1, this is 1, this is 2, this is 3, and for 4 is this, so it'd be 2, right? And then for the 2 coming in, I will swap this, so it'll be 1, 2, 6. So that will be 2. So the answer is 1, 1, 2, 3, 2, 2. Man. Yeah, this is not hard. This is not hard because longest increasing subsequence is not hard. It's just a medium problem. But unfortunately, I forgot that one again. So basically, this is the 5th time. The 5th time I have solved that problem. Dude, that was embarrassing. All right, anyway, I'll implement this later, but I'll end it right now. Yeah, basically just read this. Read the solution to this problem. Then you know how to solve the other one. All right, that will be it. I will see you guys tomorrow. Adios.